Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. Today we will continue with the topic of size reduction. In our previous classes, we have discussed about the introduction and particle size distribution, then energy requirement in size reduction, and then we have move on to the different types of size reduction equipments that we will discuss today. So, in that we have crushers, grinders and ultra fine grinders, cutting and slicing machines and homogenizers, which is for liquid foods. So, first we will see one by one that what are the different category in which we can classify the various size reduction equipments, and what are the functions and what are the speciality or characteristics of all those equipments. So, here is the flow chart which shows different kind of size reduction equipments. Starting from the left, here is a crusher, then grinders, then ultra fine grinders, cutting machines. In the crushers, we can get again different kind of crushers, which is jaw crusher, then gyratory crusher, crushing rolls. Then we have different grinders such as hammer mill, then tumbling mill, attrition mill. In the ultra fine grinders, we are getting agitated mills, and in the cutting machines we have rotary knife cutter. So, all this work on certain principle of impact, compression, shear or cutting mechanism, and most of the cases not only one single method, but maybe more than two in combination, two or more than two forces are applying in different size reducing equipments. So, if we consider the grinder, we can again classify them into intermediate grinder and fine grinders. Intermediate grinder, they produce the product which can pass through 40 mesh screen. We will discuss in detail today what is the 40 mesh screen, how this specification of mesh size has been done, and fine grinders which can pass through the product through a 200 mesh screen. And crushers are generally used for the coarse material, and they crushed into lumps. Ultra fine grinders such as agitated mill, so the feed is generally less than 6 mm and product is varied from 1 to 50 micrometer. So, we can see that there are various range of product as well as feed also. In some cases we cannot give higher size feed into that particular mill. So, now we will see in a bit detail about all such equipments. First is jaw crusher. Jaw crusher, it is a particular crusher consists of two jaws, one is stationary and another is movable. So, it moves at about 200 to 400 times per minute, and these jaws form a V shape opening with an angle which may vary from 20 to 30 degree, and solids are broken as they caught between the jaws due to compression. So, when we feed the product, we can feed by direct feeding or by hopper, or there may be some feed roll which is controlling the rate of feed, and when they come into this V shaped groove, which is having an angle between these 20 to 30 degree. So, then the solids are broken between the two jaws because of the compression force. Large lumps of solid material between the upper part of the jaw, they will come and subsequently broken and dropped into the narrower space below, because since it is a V shaped groove. So, the upper part which is having a broader part, there first the lumps are coming, and in the bottom section where the space is narrowed down, there the broken particle will drop into. Here is a diagram of a jaw crusher, and here the feed is coming into the broader section, then because of compression it gets into smaller particle, and from the narrow space at the bottom it is coming. This jaw is left one is fixed one, and this right one is movable based on that pivot joint, and the angle it is maintained as 20 to 30 degree as mentioned. There are sometimes feed roll or flywheel is provided to pass this material through the groove. So, there are maybe a different kind of arrangements, but mostly the principle will be based on compression force. The larger size particle will be reduced to a smaller size, even though this size is higher than the grinders. Then gyratory crusher. So, we can see that there is a gyratory movement that can take place in the inner cylindrical or the conical shaped portion, and from all the side, that means from the inner core and the periphery or the casing, in between these two the product is coming, and then the product is crushed and reduced in the shape. So, in a gyratory crusher, a conical crushing head gyrates inside a funnel shaped casing. So, this is our conical crushing head. So, solid cuts into the V shape space between head and the casing. So, in between these section and in between these section in the annular space basically. So, that will cut and then they will break. The speed of crushing head is 125 to 425 gyration per minute, and power requirement for gyratory crusher is low as compared to the jaw crusher. So, because of this gyratory movement, the less force is required to break this, and power requirement is also less, which is high in case of the jaw crusher. Now, moving on to the next equipment, that is crushing roll. So, in crushing roll we can use the smooth rolls. Two smooth faced roll rotates in opposite direction at same speed and size reduced by compression alone. There also can be serrated or tooth rolls. So, two serrated faced rolls rotate in opposite direction at different speed. So, we can see carefully that when we use the smooth faced rollers, so they rotate in opposite direction at the same speed, but when we use serrated roll, so they rotate in opposite direction at differential speed. So, that means all these different kind of arrangements needed for different kind of requirement, different grain size and different kind of particle size reduction. So, when we want a shear kind of effect, we apply certain differential speed, so that it will break, and then the upper surface and the lower surface will be getting differentiated. So, these are the mechanism. So, here in the second case, as I mentioned that along with the compression which was there in the first case, shear and impact will also be there. So, for the smooth roll, size reduction is because of compression alone. For the serrated or tooth rolls, size reduction is by compression, impact, and that is sudden blow, sudden high blow of force, and also because of the shear. For example, extraction of juice from sugar cane, making of food grain flakes. So, all this for food grain flakes we use the serrated kind of tooth rolls. So, these are the crushing roll. We can see here two smooth rolls are there moving at a same speed, and here we can see that there is a serrated rolls are there which is moving at a differential speed, and product coming out of that, and the grinding crushing will takes place. So, in this particular case, when we want to analyze further that what will be the angle when the product is coming in between these two rolls, we can analyze angle of neap. Okay. Angle of neap 2 alpha, which is actually angle between the two common tangent to the particle, and each of the roll. Okay. So, actually if we take certain product in between two rolls, let us say this is one roll and there is a little gap when the product will be there, and there will be another roll. Okay. So, the two common tangent to the particle and each of the roll. So, if we make that common tangent here, okay, so we can get the angle of neap, that is coming 2 alpha. Okay. So, here instead of that particle we have taken a roll which is representing the product, and here the roll of the crusher having the radius of r1, this one also r1, the second one also r1, because the dimension should be similar. Okay. And here this one is the product that is having radius of r2, and the gap between this vertical line from the center of that product to the peripheral distance of the roll, that is b, and the angle it has made at the center, the center line of this product and the center line of the roll in both the cases. So, they are making an angle alpha. Now, from the geometry of the system, that the angle of neap we want to calculate. So, the value of alpha if we want to calculate. So, from this if we take cos alpha, so cos alpha will be r1 plus b divided by r1 plus r2. So, for this one if we consider this distance and this distance, so based on that we are making the calculation. So, cos alpha equal to r1, that is the radial distance, plus b the gap, and here it is r1 plus r2. Okay. So, this we have already mentioned that r2 is the radius of feed, that any feed that we are giving in the crushing roll, and then finally the product will come out of that. So, r2 is the radius of feed, r1 is the radius of crushing roll, 2b is the distance between these two rolls. Now, if we take a problem that if crushing roll 1 meter in diameter are set so that the crushing surface are 12.5 mm apart and the angle of nib is 31 degree, what is the maximum size of the particle which should be fed to the rolls? And if the actual capacity of the machine is 12% of the theoretical capacity, calculate the throughput in kg per second when running at 2 hertz if the working face of the roll is 0.4 meter long and the bulk density of the feed is 2500 kg per meter cube. Now, we will see how we can solve this. First, we need to calculate the value of the angle alpha. So, from here the particle size may be obtained because nib angle 31 is given. Now, we need to calculate the particle size that can be calculated from this data. So, nib angle, that is 2 alpha, is 31 degree. So, cos alpha 0.964, and from here we can calculate the value of B. So, B will be 12.5 divided by 2 because this was the gap given, 12.5 mm apart. So, we are getting 6.25 mm or 0.00625 meter. Now, R1 is equal to 1 by 2, that is 0.5 meter. So, putting the value of this cos alpha, this is equal to R1 plus B divided by R1 plus R2. So, we are getting R2 as 25 mm. So, R2 was the radius of the feed. So, the feed size is 25 mm. Now, the cross sectional area for flow is 0.0125, that is the gap between these two, and the length was 0.4. So, 0.005 meter square is the cross sectional area for flow, and the volumetric flow rate will be 2 into 0.005. So, this much meter cube per second. So, cross sectional area is given, multiplied with the velocity, we are getting the volumetric flow rate. Now, the actual throughput will be 0.010 into 12 divided by 100. So, here we are getting 0.0012 meter cube per second, and if we convert this to kg per second, we will multiply this with the bulk density of this material. So, it is 3 kg per second. So, we will see if all the query has been answered. Yes, the actual capacity of the machine is 12% that we have taken. Calculate the throughput in kg per second when running at 2 hertz, that is the frequency, and okay, and 0.4 meter long, bulk density is this one, fine. So, we have calculated all the parameter that has been asked here. Okay. So, this is the frequency that has been given, this is the area. Now, from that the actual throughput will be the percentage, we have to take 12% of that. So, that is why we are getting this one, and with that multiplication of the bulk density, we are getting capacity in the actual throughput in kg per second. Now, next we will see the hammer mill. This is another size reducing equipment. So, what happened in case of hammer mill? The material is fed from top of the casing. There is a sometime there is a hopper system also to control the flow rate. Also, we can design the feeding system. So, from there it is coming and grinded by the impact of the hammers. So, the hammers will be maybe swinging form or maybe fixed with the rotor that is moving, and the grinded product is passed through the bottom of the screen. So, if we look into the diagram, so the product is coming from this upper section of from the top section. There here the blades are attached. Okay. So, this may be swinging, or that is they are freely moving or at a pivot point, or they are fixed to it. Okay. Now, when they are hitting the material, they are giving an impact force on that, then they will grind, and at the bottom there is a perforated tray by which the particles which are lower than that size will pass through, and which are not reduced to that much size will be there, and they will be again circulated in the channel unless the size is reduced to the particular size fraction sieve that is attached at the bottom section. Hammer speed generally we keep 1500 to 4000 rpm and use for poultry feed grinding, spice grinding, etc. Also this kind of hammer mill is used for the millet grinding operation. Now, advantage is that less chances of the damage of the mill, and disadvantage is high power requirement needed for running a hammer mill. Now, tumbling mill. Tumbling mill is a cylindrical or conical shell rotating about its horizontal axis, and half of its volume is filled with grinding medium, that is rods or balls. When we use the rod mill, rods of dia 25 to 125 mm, and here in case of tumbling mill, the compression force and attrition force. Attrition because there is a rubbing effect between the rods or the balls that has been given there inside the mill. So, because of that attrition effect is also coming. Then when the mill is rotated, the balls are picked up by the mill because of the motion, rotating motion, and so the mill valve will take them up and carried nearly to the top, where they break the contact with the valve and fall to the bottom of the cylinder by gravity. So, most of the reduction is done by impact of the balls. Okay. So, rod mill and ball mill that we have seen. In case of the rod mill, we have seen that compression and attrition, and when we use the ball mill, we are getting the impact force along with the attrition effect. So, if you see, this is kind of a cross sectional area we can view, where almost half is filled with balls, okay, and as this rotated, so this balls are from the horizontal section to this upper section, it is picked up, but since it is half filled, and then when it rotates to the other section, this balls will again try to fall down, and because of that impact the product will be grind, and also the effect of the attrition. If the speed is too high, however, the balls stick to the wall and not release from the top, so no impact occurs. So, this condition is said to be centrifuging. Okay. So, as I have shown you that this kind of a effect is there when the speed is reasonable, that means not very high and not very low. So, the balls will come with the rotational speed and stick to the wall up to certain extent, then they will drop, and while drop they will force the impact on the product, and while moving inside they will give the attrition effect, and this is the last one is the centrifuging effect, when because of very high speed the balls are stick to the wall, not coming to the bottom because of gravity. Okay. So, this fall will take only when the force on the particle because of the rotational movement will be lower than the force of the gravity, but in this case the gravity force is lower than the centrifugal force that those particles are getting. Now, the speed at which the centrifuging occurs is called the critical speed. So, here we can see in actual case how it looks like when it is filled with the balls. Okay, this is the driving gear at the top one, this is the feed inlet, from here we are sending the material, and this is the product outlet. There is a conical grate given, and the size of the balls is also differ. Here the larger balls are there and the smaller balls also is there. Now, we need to calculate the speed at which it should run properly. So, that is called the critical speed, that is denoted as NC in revolution per second, that is equal to 1 by 2 pi into root over g by capital R minus small r, where g is the acceleration due to gravity in meter per second square, and capital R and small r are the radius of the mill and the ball in meter. Rotational speed of the ball mill for wet and dry grinding are 65% and 80% of critical speed respectively. So, in case of wet grinding, the speed will be 65% of the eta NC, and for the dry grinding it will be 80% of the critical speed. Now, we will see that how we have derived that critical speed formula. So, for that, see here we have a cylindrical section, the radius of r, which is denoting the radius of the cylindrical section, and small r, there is a small ball at the top end. If you can see, this is the small ball whose radius is small r. Okay. Now, these balls are rotating. Okay, these are rotating along with the cylinder that is rotating. When it comes to the top section, okay, gradually when it comes to a certain section, always its gravitational force acting downward. Okay. So, this diagram has been taken from Macbeth-Smith, and then everything has been given in FPS system, but you can take this as mg only instead of mg by c. So, this is the downward gravitational force is coming, and here mv square by r, that is the centrifugal force is acting on the particle which is in the outward. Okay. So, this particle has a tendency to go outward or to throw it to the outward direction based on this force, and it is also having a downward force, that is because of the gravity. Now, if we split this force in, if it makes an angle with the line joining the center of the mill to the center of the particle. So, the angle it will frame, let us say this is alpha. So, we can divide this force mg to mg cos alpha and sin alpha. So, mg cos alpha will be just opposing to this centrifugal force. Okay. And the distance from the center of the mill to the center of the ball will be capital R minus small r. Now, centrifugal force is omega square r. So, omega square r is here, r will be capital R minus small r, because that is acting on this particle at this distance. Okay. So, omega equal to 2 pi n. So, we can write 4 pi square n square into capital R minus small r, and component of this gravitational force, which is mg cos alpha, acts opposite to the centrifugal force. Okay. Now, there will be one situation when this will come further in this direction. These two forces are equal. Okay. So, if we consider that, that means there will be alpha is equal to 0 degree. So, cos alpha is 1. So, when this farther goes to the towards more right. So, then a condition will arise where alpha is 0. So, we can take straight away m g cos alpha equal to 4 pi square n square into capital R minus small r, and at that condition it will be a critical speed, n will be n c, that is critical speed. So, n c will then we can get out of this to equating m g with 4 pi n square capital R minus r. Okay. So, m g with m v square r. So, then we are getting m v square by r. So, then we are getting the critical speed n c as this way. So, basically what we are doing, we are equating that m v square by r with m g cos alpha. Your cos alpha is 1 because alpha is 0 we are considering. So, here this r is actually capital R minus small r, because we need to take the center of the mill to center of the ball. So, this is how we can calculate the critical speed of the ball mill. So, we will stop here and we will continue in the next class. Thank you.